Hi, I'm Sijie from Shanghai Jiao University. It's my pleasure to introduce our work about retrofitting high availability mechanism to tame hybrid transaction analytical processing. This work is advised by Rong, Haibo, and Binyu. For database systems, OLTP and OLAP are two typical workloads. OLTP is a series of short-term read-write transactions used in order processing or e-commerce, while OLAP consists of long-term read-only queries such as BI or data mining. HTAP is a new workload called Hybrid Transaction Analytical Processing. For HTAP workloads, queries are processed on real-time data generated by transactions. HTAP is the key process in many scenarios like IoT, healthcare, fraud detection, and recommendation. Performance and data freshness are important requirements for HTAP. For performance, an HTAP needs to minimize performance degradation, even facing with millions of transactions per second, such as a shopping festival of e-shops. For freshness, lots of applications require sub-millisecond of data delay between TP and AP. For example, fraud detection and system monitor needs 20 milliseconds of time delay. A traditional data flow of data analysis is OLTP, ETL, and OLAP. First, data are generated by update, delete, or insert operations on OLTP databases. Then, it sends the updates to the ETL component to transfer the data from row store to column store. And then the data will be stored in the OLAP databases. We call this alternative as dual system. It has good performance on specific systems, while the time delay of ETL is usually from seconds to minutes. Performance and freshness is a difficult trade-off among HTAP architectures. We summarize the current HTAP systems into three alternatives. Dual system has good performance and a large time delay as we introduced before. To shorten the time delay, the second alternative is to execute both of AP and TP on the same data layout. Obviously, the performance prefers to the one-off types of workload and has serious interference. The third alternative executes OLAP and OLTP on different layouts of a single system. However, the trade-off still cannot match the current requirements. To achieve both good performance and freshness, we present a distributed in-memory HTAP system called Vegito. We observe that the high availability mechanism for fast in-memory OLTP systems gives the opportunity. Replication-based HA is common and send synchronized log during transaction committing to sync data between primary and backups. Backups for TP guarantees freshness and fault-tolerant. Vegito reuse HA for HTAP. Briefly, it can execute OLTP on primary as before and transfer one of backups to backup for AP, which can execute queries. Vegito provides a fresh, fault-tolerant, and columnar backups for AP. Vegito can achieve a better performance freshness trade-off under the millions of transactions per second. To provide the freshness, fault-tolerant, and columnar backup AP, we face some challenges. Next, I will introduce the challenges and our designs. The TP threads will append logs to the queues on the backup AP, and the cleaners on backup AP will drain logs and write the updates on column store and index. The AP threads will read column store and index for OLAP queries. For high availability, cleaners drain logs in parallel, and it does not consistency until recovery. However, AP queries need a consistent view on backup AP. A naive design using global timestamp and sequential cleaning will drop the performance by about 70%. So backup AP needs consistent and parallel log cleaning. Vegito uses a Epoch-based design to overcome the challenge. It partitions time into non-overlapping epochs and gives a time isolation between OLTP and OLAP. Each transaction will write logs with an epoch number. The number will increase periodically. Each query will use a query epoch to read the stable version of values on the backup AP. And there is also an epoch for cleaner. It means the epoch of logs being drained. In this design, the interval between these two types of epoch determines the freshness of system. So we need to provide a millisecond level epoch with consistency of distributed transactions for freshness. For consistency, an epoch oracle is responsible to update the epoch number periodically and broadcast it to nodes. For some rare cases, the epoch number will violate the dependence. For example, the transaction 2 on machine 1 depends on transaction 1 on machine 2. However, the epoch of transaction 2 is smaller than transaction 1. Transaction 1 will gossip its latest epoch to machine 1. This gossip-style mechanism guarantees the epoch assignment is consistency. Through our design, the epoch specifies that provides transaction within an equal or smaller epoch, which guarantees the consistency. By epoch number, Vegito can clean logs matching transaction dependence. All logs with the same epoch number can be drained in parallel. When the cleaner on a machine have drained all logs of an epoch, it will update EC, means epoch for cleaner, individually. A distributed query will use the minimal EC as the stable version for query. The second challenge is how to guarantee both the read and write locality on column store. In Vegito, we use a multi-version column store for isolation and OLAP performance. Read operations prefer column-wise locality, while write operations prefer row-wise locality. A widely used structure of MVCS is Chen-based. Its update is efficient. However, the scale operation on an old version will drop the performance by 90%, while read half more versions on average. To exploit the performance for OLAP, Vegito uses a block-based MVCS. It is efficient for scale operations and update by copy on write in the unit of blocks. To avoid the blocks too large block size, we introduce two kinds of optimizations, row split and column merge. They split a column into several pages and merge high-related columns together. The block-based design with optimizations can improve scan performance compared with chain-based MVCS. The third challenge is how to guarantee both the read and write parallelism on the tree-based index. The performance of tree-based index will influence under heavy update workloads. Write-optimized and read-optimized tree-based index will sacrifice the performance of another side. The insert operation can be split into in-place insert and strict balance operation. The balance operation is costly, so we insert values in the buffer on each leaf node and balance them in batch. This design can exploit the performance both on the write operation and read operation under the Epoch-based designs. The backup AP can still provide the fault-tolerance. Vegito preserves the same availability guarantees and doesn't need extra replicas. Vegito prefers to recover the primary from the backup TP. There are some special cases. When both primary and backup TP fail, Vegito rebuild primary from backup AP and migrate to another machine. When backup AP fails, Vegito rebuild it to the next epoch. We conduct our evaluation on 16 machines and choose CH benchmark as the benchmark, which is a hybrid of TPC-C and TPC-H. We have 3 kinds of workloads: OLTP only, OLAP only, and HTAP. We set the epoch interval as 15 milliseconds in Vegito. Vegito can be comparable with the specific systems. For the OLTP only workload, the peak throughput is 3.7 million transactions per second, which is 1% lower than the state-of-the-art OLTP specific systems. And for the OLAP only workload, the Jiao mean latency of Vegito is also comparable with the state-of-the-art OLAP specific systems. For HTAP workloads, Vegito can achieve both good performance and short freshness. It can execute 1.9 million transactions and 24 queries per second simultaneously, with the freshness less than 20 milliseconds under our configuration. In the fault-tolerance experiment, we kill one of the primary for twice. It uses about 42 milliseconds to rebuild the primary from backup AP. To conclude, we present an HTAP system called Vegito, which retrofits high availability mechanism to Tame HTAP processing. We provide a freshness columnar and a fault-tolerant backup AP. It can execute OLTP on primary and OLAP on backup simultaneously. Vegito is also open source on GitHub. Thanks for listening.